it's a pleasure to be here. So when I was growing up, I've sort of been a physicist at heart for a long time, and I was fortunate. My father had this big shelf full of really interesting physics books, black holes and parallel universes and time machines and stuff. And there was one of them, there was one there that was entitled, "What is the world made of?" And I thought, boring. It's made of electrons and protons and neutrons. I knew that then. Let me move on to the multiverse. But in fact, the idea that the world is made of kind of particles was a really, really profound one. It took us from the idea that things were made of kind of different substances to this idea that they were made of particles and fields. And from the electrons and neutrons and protons to quarks and leptons of various types, the Higgs boson that was just discovered. And this standard model of particle physics is an extraordinary thing. It developed over decades. It explains so much. It is perhaps connected to some deeper theory of string theory, other theory of everything. It lays a foundation for chemistry and biology and so on. And we also have this standard model of cosmology, the Big Bang model. It may connect to some earlier, deeper theory of inflation. That's my specialty. It lays a groundwork for understanding elements and galaxies and stars and planets and us, how we formed through this 13.8 billion years of cosmic evolution of the observable universe. These theories, in fact, are in a bit of a crisis, not because there are things that sort of contradict them, but that they're so successful that we can't find new things to kind of give us more information about how to go beyond this standard model and the Big Bang model. So they're incredibly successful, and yet I was delighted to hear in the last discussion, there's still this question, what is the world made of? What are these particles? If we think the world is made of particles and fields, what are they? What is an electron, right? This is a question from the last one. What is really an electron? And when you study this, as a physicist, you study this in school. In high school, you might learn that an electron, or middle school, that an electron is something with a charge. You might learn in high school that it has spin. It's a little spinning charge. You might learn in college that it has electronic lepton number of 1. But then when you go to grad school in physics, you learn field theory. And you learn that an electron is an excitation of the electron field, okay? Like a photon is an excitation of the electromagnetic field. So this feels really good. You understand what an electron is. It's an excitation of this field. If you ask what the field is, you're told, well, the field is something that makes and destroys electrons. And so that kind of leaves you nowhere. Mathematically, it's a beautiful self-consistent theory, but what is the electron still? So quantum theory tells us something even a little bit more mysterious in a way. An electron is something that acts like an electron when you do experiments. And when I first learned this, I was really troubled. I think something looks like a rock because it's a rock. It's not a rock because it looks like a rock, but maybe quantum mechanics is telling us something about that. So let's talk a little bit about quantum mechanics. What does quantum mechanics really mean? And I think it can be put fairly simply in some sense as follows. When you talk about something having a quantum state, like an electron in an atom, what is a quantum state? Well, it is a complete list of questions about that system and their definite answers. One question might be, what is your position? Here it is. What's your energy? 53 electron volts. Are you spinning clockwise? No, I'm not. So there is a specific set. You can't ask any more questions and get a definite answer to them. It's a complete list. But there are some extra rules. If you come upon a system in some state, you can't know what the right list of questions is. You can ask questions, and you'll get answers, but you can't know what the list of questions was that came with the particle. So if you ask a question that doesn't have a definite answer, you'll get an answer. Nature will answer you. But you won't get one with a definite answer. The answer will be indefinite, and nothing, as far as we know in quantum mechanics, determines what that answer will be. It just gives you an answer. But once you've got that answer, if you ask, it's real. If you ask the same question right away again, you'll get the same answer. So that there is a reality there to the thing. You've learned something about it, and you've also changed it, because now it has a definite answer to that question. That wasn't one of the questions that you could have a definite answer to before. You've given it that one, so you've changed the quantum state. Now it's in a new quantum state. And this is kind of the essence of quantum mechanics. But although the quantum state contains everything that can be known about the system, it doesn't necessarily contain everything you might want to know about. You can ask it lots of questions you might want to know the answer to. It will give you answers, but they won't necessarily be definite ones. But a wave function tells you what it can tell you. It'll tell you probabilities for the outcome, for the answers to the questions you're asking. So this is a wave function, an actual one of a particle, an imaginary particle in a little box. It has a specific energy. If you asked it, what is your energy, it would give you a specific answer. But if you ask it, where are you, you could get lots of different answers. The answers you can get, though, have probabilities. It isn't definitely not in the middle of the box. It might be like a third of the way or 2/3 of the way through the box with reasonable probability. So the wave function gives you probabilities. And the wave function changes in time. There's an equation that tells you how the wave function changes in time called the Schrodinger equation. And that's how the world evolves. The wave function changes in time. And that's kind of it. Now so the wave function is information about possible experiments that you can do. Okay, that's fine. But the perplexing thing, the thing that people have sort of spilled so much ink over and worried so much about, is that it seems like that's all that there is. It does not appear that there's something else that the wave function is about, that the electron is there and the wave function is describing it. The electron, it seems, and people disagree about how to think about quantum theory, but all the basic interpretations agree on this, that the electron is in some sense made of wave function. And what is wave function? It is information about possible experiments. So the electron is made of information about experiments that you might do. So what does it mean for something to be made of information? Well, actually, that's not so weird. We know lots of things that are made of information, like Hamlet is made of information. You might read it on your Kindle, or you might read it in a book, you might read it on the internet. Very different forms of that information can take, different sort of encodings of that information. Hamlet itself is made of information. You don't really care which form it is at some level. If you scramble the words around, you don't have Hamlet anymore. If you translate it from the Kindle to and print, take it from the internet and print it out, you've still got Hamlet. It's made of information. We're less sort of comfortable with saying that a praying mantis or an airplane is made of information, but they are too, I would say, in the same way. If you take all the atoms in an airplane and just scramble them up and give them to someone, you haven't given them an airplane, right? You've given them a mess. So the thing that makes it an airplane is the structure. The thing that makes a praying mantis instead of a bunch of goo is the structure. Even at the deepest level, new understanding of how space-time works suggests that sort of space-time itself is made of information. So what is information? It's sort of like saying everything is made of purple goo. That doesn't mean anything if you don't say what purple goo is. So one way I think to think about information that's pretty general is that information is kind of the difference between how generic some system is and how generic it could be, the possible genericness. Genericness here is a sort of less technical word for entropy for the physicist. And if you have something that's completely random, kind of completely generic, there's no information you've got about it. If something has zero entropy, it's completely settled, that means you know everything about it. You've got a ton of information about it. So for example, if you have just a string of bits, 100, 111000, generically, so strings of bits that have like half ones and half zeros, they have high entropy. You don't get any real information out of it. If you see a string of bits with all zeros, you know exactly what string it is. It's that one. There's a lot of information in that string of bits. Regular physical systems are far from equilibrium. We're far from equilibrium. This jungle is far from equilibrium. Tons of information. In fact, a lot of the thing that living beings do is prevent themselves from going to equilibrium. When they die, they kind of go to equilibrium in a physical sense. Metabolism and like finding food and all the things that physical beings do is largely to keep their information, to generate information to keep from going to equilibrium. The wave function for a quantum state, that contains a ton of information because it tells you exactly what the state of, it tells you everything you can know about a system. But information is a kind of funny thing because it's a little bit in the eye of the beholder. You know, why does this string of zeros have information but the other one didn't? It was kind of a simple one. It was very non-generic. You can tell, say, a picture has some information in it. If you run it through zip, it will get smaller. If you run like a random bit of noise through zip, it won't get smaller because there are patterns in a picture that the compressor can use to make that file smaller. It can identify those the same thing, in the same way that you identify patterns and things. You can print out all kinds of strings of musical notes. Very, very few of those strings are music, right? And very, very few of those strings are Bach. There's something that we put in. We decide what is interesting, what is quality music. We've created information by making that decision. Or math, you could have a computer that just spits out zillions and zillions and zillions of theorems from some set of axioms. Most of them would be super duper boring. Only a very tiny amount would actually be what we call like interesting math, and only a few would have the elegance of, say, Stokes' theorem. So information is something at some level that we identify and that we create. And yet it's very real because remember, information is like the opposite of entropy. Entropy is one of the realest things there is. The second law of thermodynamics is probably one of the most inviolable laws of physics. If you think you can violate the second law of thermodynamics, I've got like a time machine and a perpetual motion machine I'd like to sell you after this talk. You can't be done. So information is both this super real thing, but also something that we as conscious beings seem to invent. Now, information happens at different levels, and you can sort of see, if you look at this bit string like I had before, it could be that each one of those bits is made up of a whole bunch of smaller bits, like if there are more than half ones, it turns out into a 1. If there are more than half zeros, it turns into a 0. And the physical world seems to have this property. It has information at all different levels. You might, for example, send smoke signals. It's a very terrible way of communicating. You get a few bits of information across, but it can work over long distances. So the information kind of shared between the smoke signal sender and receiver is just a few bits, right? But if you actually look at the correlations between the particles of smoke and the particles of matter in your eye or your brain, there are tons of information that's shared between them. So that tons of information is kind of coarsened and smoothed over to provide just a few bits at a level that we understand the smoke signal. We can't perceive all the information at that fine-grained level, but we can perceive it at the level of the smoke signal. There seems to be kind of deeper and more fundamental levels of information that underlie the coarse-grained ones that we observe, but they're both important. Now, if you think about this idea of there being sort of more fundamental and less fundamental things, there's kind of this interesting divergence that takes place in our conception of the world. So as a physicist, there's kind of this ideal that we want to study these really mathematical, these really fundamental things, fundamental physical theory. I like to call it sometimes the unitary relativistic block. And it has things like the manifold, metric, quantum states, Hamiltonians, fields, actions, symmetry groups, all this technical stuff, mathematical laws, very divorced from the reality that we actually experience, the flow that has the flow of time. It has objects and perceptions and agency and choices, memories, dreams, reflections, meaning, understanding, qualia, things that you feel. And there's a huge gap between these two in sort of our present conception of physics. There's this idea that this is sort of more, the relativistic block is more fundamental. That's what we call fundamental physics theory, and this other stuff is kind of derived from it or emergent or something like that. And why do we think that way? What do physicists mean when they say something is more fundamental than something else? Well, one way to think of it is that physicists like to say that once you decide the fundamental thing, you've determined the fundamental thing, then that also determines the less fundamental things. So for example, if you decide that you have the standard model of particle physics, that gives you the laws of electricity and magnetism, that determines how circuits work. Once you decide on the basic model of particle physics, circuits can't work any other way. They're fixed. You can derive one directly from the other. Or if you know Einstein's theory of relativity, you can derive Newtonian gravity, and you can derive from that the dynamics of planets. One just follows from the other. Once you fix one, the other follows, and you can't get around that. And to some level, that's true. So there are sort of successful reductions, I would say, that say you fix some more fundamental theory and you get out this less fundamental experienced reality. But there are lots of ways, and this is, I think, is really becoming more and more clear to me and more clear to physics maybe as time goes on, that the physics does not do this. This relativistic block does not determine everything. Why are there no dinosaurs? Why are there no dinosaurs? The relativistic block won't tell you that. There are dinosaurs, there are no dinosaurs all in it. The reason there are no dinosaurs is because we're here and now. This is information that we put in to the theory to get something useful out of it. The quantum wave function tells you probabilities. This might happen or this might happen. The relativistic block tells you both. Only one of them actually happens to us. And so that's information. Out of all those possibilities for what happens, there's information about what actually happens that we put in. So there's information we put in. It's not even clear that things like chemistry begets biochemistry, begets biology, begets neuroscience, and so on. This is an idea, but it's not at all clear that you can actually get one from the other. There could be ingredients, there could be strong emergence or sort of historical contingency that comes in. It's not clear that neuroscience, that once you fix chemistry, that neuroscience really has to act exactly the way that it does. So I prefer, rather than thinking of these two poles, because we like to polarize things, that it's sort of useful at some level to think of a kind of spectrum from the more subjective to the less subjective. Oops, I put more subjective both directions. The left should be less subjective. More subjective and more objective on the right. So the spectrum of objectivity. It's a real word. It's a real word. Trust me. And you can sort of put all kinds of things on there. So me-ness, the feeling that I have that I am me, is a very personal, subjective thing. My music preferences. A little bit wider, shared with more people, are social norms. A little wider, universal human rights we might all agree on. Money, sadly, seems more fundamental than universal human rights. But it really works. If you don't obey the rules of money, you will pay for it. Living things have maybe some sort of reproduction. They share some survival instinct, and so on. We can go all the way down to seemingly very objective things like the Pythagorean theorem or the second law that are very mathematical in nature. And we might feel like even aliens, if we found them someday, would agree on the Pythagorean theorem with us. But people, we really like to identify things with ourselves. We really like to smush things over and say, my musical preferences are right, other people's are wrong. The social norms that I like are universal sort of moral truths. The things that I see are really out there. They're for real. They're not things that I made up, even though they probably are. And I think both science and certain spiritual paths are a great antidote for that. They help us see that everything isn't about us, and that the reality that we see is not a true reality out there. It's something that we sort of made. On the other hand, there are overzealous reductionists, I would say, I know lots of them, who feel like if we just knew the wave function of the universe and the fundamental theory of everything, we could derive all of this stuff. If we were just, had a big enough computer, we could figure out eventually Anthony's music preferences and so on. So there are people who would like to push it to both poles, but I think it's useful. And I think there's some measure of wisdom in really trying to understand and have a clear view of what falls sort of in what category, which is tremendously difficult to do. But I think as you contemplate it, you sort of learn something about how to act in the world. And I think as a tool that can help that is that, as I mentioned, I think all of these can sort of be thought of as different forms of information. That there's personal information, that Facebook gathers up. There's all the way through mathematical information. Out of all the possible mathematical theories, which are the ones that we find interesting, and everything in between. And so I think, in answer to the question of what is the world made of, I think we're really coming to a place where rather than thinking of it as just substances, sort of true, just particles and fields, quite true also, but maybe the world fundamentally is, in a lot of ways, made of information. I think that may be the way that we start to think about it. Now, who is it that knows that information? I'll leave that as a question for us to think about later. Thanks.